All right, you've probably seen the headlines swirling around this new model, DeepSeek-OCR. And for good reason. The claims being made are, well, pretty out there. We're talking about a technological leap that, honestly, seems to bend the rules of what we thought was possible.
So get this. One of the wildest claims is that DeepSeek can shrink data down to 1/10 of its original size. People are talking about cramming tens of millions of words into a single context window. And that's the kind of thing that makes you just stop and ask, wait a second, is that even allowed?
And that right there is the big mystery we're going to try to solve. You see, according to the literal laws of information theory, there's a hard physical limit to how much you can compress something before you just start losing information. It's a thing called entropy. So the real question is, how did DeepSeek pull off this magic trick?
To get to the bottom of it, we need to take a quick step back. We got to talk about the fundamental difference between how you and I see language and how a computer sees it. Because that difference, it's the key to this whole puzzle.
Think about it like this. When you hear me speaking, your brain is just naturally putting together sounds and finding the meaning. But if I suddenly switch to a language you'd never heard before, it would just be noise, right? The sounds don't mean anything on their own. We give them meaning. Well, computers have that exact same problem with our text.
So what do? To help computers out, we came up with this system of breaking our language down into little pieces called tokens. You can think of a token as just a number that stands in for a word or even just part of a word. It's the basic building block that AIs use to process our language.
And this is absolutely crucial. We designed this whole token system to make language easy for computers to calculate and to scale up. The goal was never, ever about storing language efficiently. It was all about making it computable. And that one decision created a massive bottleneck.
Which leads us right to the heart of the problem. This is the very limitation that DeepSeek had to figure out a way around, the tokenizer bottleneck.
Hey, remember that impossible limit I mentioned a minute ago? Well, it has a name, symbolic entropy. It's a real scientific principle that basically says there's an absolute limit to how much you can compress a system of symbols, like our tokens, before you just lose the meaning. It's the rule that DeepSeek looked like it was breaking.
Let's make this super simple. Take the sentence, Caleb writes code. Once that gets turned into tokens, let's just pretend Caleb is token 100, writes is 59, and code is 67. That's it. It's done. You cannot compress that string of numbers 100, 59, 67 any further without just losing the original words. That is the hard wall of symbolic entropy. So the main takeaway here is that our token-based system is super rigid. Information gets chopped up into these separate, unsquishable little numbers. It works, for sure, but it's not exactly what you'd call information dense when you think about other ways you could represent data.
Which, of course, brings us right back to our big question. If there's this hard limit on compressing tokens, how in the world did DeepSeek pull off a 10x compression?
The answer, as it turns out, is one of those brilliantly simple solutions. It's a perfect example of not trying to break down the wall, but just walking around it.
And here is the big reveal. DeepSeek didn't break the laws of information theory. They didn't invent some magical new way to compress tokens. They just stopped using them. They completely sidestepped the entire problem by changing the medium altogether. They went from text to images.
Okay, so here's exactly what they did. It's pretty straightforward, really. First, they used a vision model. Then, they treated a whole page of text not as words, but as a single picture. And third, they compressed that picture into something called a latent space. You can think of that as just a super dense mathematical summary of the most important parts of the image.
And the result of this little paradigm shift? A mind-blowing 10 times improvement in what we call representational efficiency. And just to be clear, we're not talking about making file sizes smaller on your computer. We're talking about packing way, way more information into the same amount of space an AI can actually process.
And the results are just nuts. At that 10x compression level, the model was still 97% accurate at rebuilding the original text from the compressed image. And even when they pushed it to a crazy 20x compression, it still managed to hang on to 60% accuracy.
Now, this idea didn't just pop out of thin air. The AI visionary Andrej Karpathy has been saying for years that tokenizers are a dead end. He famously posted, "The tokenizer must go." Well, it looks like the team at DeepSeek was paying attention.
So, what does this actually mean for the future of AI? This clever sidestep, it might be more than just a neat trick. It could be pointing to a really fundamental shift in how we build and talk to our AIs.
Now, it's really important to get this part right. DeepSeek didn't invent some revolutionary new piece of tech here. The model itself is a smart combination of technologies that already existed. The real genius wasn't in the individual parts, but in how they put them all together to solve this old problem in a completely new way.
And the ripple effects from this could be enormous. I mean, this could completely upend the field of context engineering, which is where a lot of AI companies have built their entire business model. We might be stepping into a whole new era where feeding AI an image of text is just the normal way to do things.
Which leaves us with one last, kind of wild thought. I have a friend who swears he thinks in pictures, not in words, which, as someone who definitely thinks in words, I can never quite wrap my head around. But looking at this, you really have to wonder, are we on the brink of teaching our AIs to do the very same thing? And if we are, how is that going to change, well, everything?